Hold on, I'm almost done with this house clip. 1 minute and 30 seconds left, okay?
She's incredible.
Thank you.
Head.
Why? I don't understand why there are times in the show where people are like, oh, I approved it just because it was a house, even though there was no medical reason. But they're like, but there was. Like, how does that make sense? Are you here for GTA 6? Maybe. A record docs released at like 10 p.m. last night. Yeah, I saw. Now that we got all that out of the way, now we just wait for the judge to start ruling on stuff.
Get down! Do it now!
Is it 9mm? That is, right? Or was that 40? What is this? Is this a new gun, or is it just like a huge modification of like a Glock or something? That's 9mm? Okay. Why is the black one? Yeah, I don't know why it is that color. What the fuck? It's a chassis for either a Glock or a SIG. Gotcha. Okay, where's the long-haired physics guy? He's in YouTube chat all the time. Is he here right now? Fuck. Okay, he'll show up later. I'm trying to read up on random shit that gets brought up in random debates all the time so that I feel like I actually have a better understanding of them instead of not understanding it at all. I feel like I've used these words before. I don't know if I've ever referenced this or talked about it with more specificity. Yo, this shit, you ever heard of this thing called you ever heard of this crazy dude called the Double-Slit experiment? Yo, that's some wild shit. What's going on there? What's going on with that? What's going on with that? That's... When people say the wave-particle duality, what does the particle part mean? I feel like I understand the wave part. Is the particle is it because you can measure like individual electrons, or what does that mean? What is the particle part of that? Ask Reason Riffs? Yeah, I asked for him earlier, but he's not in fucking chat right now. It's severely misunderstood. Watch a video on it. So I have watched videos on it in the past. And then I tried to watch like a... Professor Dave Explains video.
Welcome to Professor...
I think he has one. And it has 1 million views.
Professor Dave here. Let's talk about the double-slit experiment.
He knows a lot about the science stuff. Professor Dave explains.
In learning about the first few discoveries that led to the development of quantum mechanics, we discussed wave-particle duality. So we understand that both light and matter behave as both particles and waves. But we glossed over some of the technical details, so let's zoom in for a moment. In 1801, Thomas Young performed experiments where light was passed through a plane with 2 slits in it, striking a screen beyond. The diffraction and interference patterns that resulted clearly supported the wave model of light, with the brighter bands representing constructive interference and the darker bands representing destructive interference, with the width of the bands being a function of the frequency of the light. Later in the century, Maxwell showed that light is a wave of oscillating electric and magnetic fields. So it seemed as though the case was closed on the declaration of light as waves. But as we said, in 1905, Einstein solved the problem of the photoelectric effect by assigning particle nature to light. Thus, wave-particle duality was born. Later, de Broglie proposed that particles must therefore also display wave-like behavior, and this was shown to be true in an experiment, just like Young's more than 100 years prior. This modern version is what we are typically referring to when we talk about the double-slit experiment. From this, it was shown that a beam of electrons exhibits diffraction and interference patterns, just like light does. This demonstrates the wave-like properties of electrons, and by extension, matter in general. Later, low-intensity experiments showed that even an individual electron, when passing through biprisms or slits, will interfere with itself, making the wave-like nature of the
I love how this is the worst possible visual that you could use to explain this.
electron undeniable. So it was shown that electrons act as both particles and waves.
Okay, I listened to these videos and I never really, I don't know, I just, okay, I guess. I don't know, I don't know, I don't care much, okay? So, but for whatever reason, I was bored last time. I was like, it's time to read some Wikipedia. But it actually seems like very crazy or weird. And then I think I feel like I have like a slightly, when I say slightly better, I mean like a 1 to 1.5% better understanding of maybe what is implied by like the many worlds or infinite worlds interpretation. Okay, all right, hold on. Okay, check this out. Okay, this is actually this is wacky, wild stuff. All right. Okay, first thing is, where's that physics guy? He's gonna show up later. I just have I have one question, and I'm sure there's a ton of questions. There's just one thing I want to know. Okay, we'll get there. Okay, all right. When you have I don't remember what this is called. It's like linear equations, 1 dimension, 2 dimension, some bullshit. You have these things, okay? You got okay. When you have two waves and you play these waves on top of each other, it always results in, it's called interference, and you can have constructive interference and destructive interference, I believe, right? So constructive is when, I don't know if you would say the peaks of the waves or whatever mesh in such a way that the amplitude is greater when you've combined them. Destructive interference, I think, is when the amplitude is reduced, having to do with like the phasing. So like in a perfect world, I think let's say that you have like one wave that does this, and then let's say that you have the exact same wave, but it's like out of phase. So you flip it. How do I flip this? Blue? Wait. When you would play these over each other, this would be like a perfectly destructive pattern. It would average out to 0, right? This would be destructive interference. So ideally, this is how noise canceling headphones would ideally work with like ordinary sound, right? Okay, so you have these interference patterns, right? And anytime that you shoot waves at each other, they always have some kind of, there's always some interference pattern that's created, okay? Okay, so if you shoot, anytime light comes from an area, there's always, light always moves in waves, right? You know this, we all know this, that if I were to shoot a beam of light at this hole, the light doesn't come out like this. The light comes out like this. It comes out, it emits from the hole, like in a wave kind of, right? Now, because this hole is not like a single point in space, because the hole has a range, right? Technically, I believe what's happening is there's many different waves that are all coming out from this thing, and all of these waves will create a diffraction pattern on a screen back here, such that you'll have like Like it's really bright like here, and then you move, and I don't know if there's a name for this, but you kind of move off and there's like another pattern kind of like here, because these waves are kind of having interference with each other, basically, right? Which that makes sense to me, okay? I think, right? Okay, cool, because it's all waves and oscillations in, what is it, magnet and electricity or some bullshit, however electrons work, whatever. It's like, okay, right? This makes sense so far, right? That you get this little pattern. Wait, where is the single slit? Single slit experiment. What does it look like? This. You get like this diffraction pattern that's caused here, right? Okay, makes sense. Probabilistically, you can, you know, think of like where the electrons end up. No, you don't think about that probabilistic, sorry, because you're just looking at it as a wave, okay? All right. However, okay, so then there's one more thing, which I feel like is weird, okay? If you do this same experiment, but you do it with two slits, so now you're emitting like this, okay? Not only do you get a diffraction pattern here, my physics, like sound understanding would be diffraction patterns happen as a result of waves like messing with each other. However, so my guess would be that if you were to shoot a single electron into this, that a single electron would go through, and then a single electron would just build up right here. That would be my assumption, right? On an experiment like this. Like if you shoot like one electron here, then you shoot one electron here, and then you shoot one electron here, and then you shoot one electron here, it's just going to build up like this. You're just going to have two dots on the thing. But that's not true. Even if you're firing single electrons, they still arrange themselves back here in a diffraction pattern. Why? That's wild. How does that happen? What are they diffracting with? What is interfering with it? I don't understand. That's wild. This video goes over your questions. I've watched videos on this before, and I've never even come remotely close to having any kind of understanding of this. Ironically, it was reading the Wikipedia last night that I started reading. I was like, oh shit. I was like, that's some crazy shit, actually. It's actually some crazy shit. And so I think, I'm stretching a bit here because obviously this is way outside of my, but so like I think the many worlds interpretation, the idea is that the interference is happening with itself through all universes at all time, but when you measure, or when a measurement happens, then that's just one possible outcome of every other possible outcome that's also occurring simultaneously, and that's why it's able to cause an interference with itself, I guess, is one possible interpretation. But, right, maybe, but I just don't understand why. I just need the physics guy to explain that to me. Why, when you shoot a single electron, why does it cause a diffraction pattern? Destiny, to be clear, sending in electrons one by one gives that interference pattern in aggregate. It's not one electron making the whole interference pattern. I understand that, but my assumption would be that if you shoot a single electron in here, it would just be here every time. Or if you shoot a single electron in here, then a single electron would spread out like in a normal distribution, I guess. So it would look something like this. However, a single electron over and over again doesn't cause this. It causes a diffraction pattern, like there are waves that are interacting with each other. I thought we can't measure a single electron. We didn't measure a single electron since like 1987, okay? What debate does this possibly come up in? I don't think it does. I feel like sometimes people mention random things like, oh, the double-slit, and I would just like to.
As a 40.
Okay, let me see if I'll watch this. I feel like I've watched so many videos on this. I've never really had any understanding of this at all before. Like, I understand you guys keep saying that particles behave as waves too. That's a statement that I've probably even said on stream before, but that doesn't really make, that's like a super loaded statement. I've never understood like, oh, particles behave as waves, LOL. But to think that like a single particle could behave as a wave that could cause a diffraction pattern with just itself, that's like a really, I feel like there's a lot of very crazy things going on there for that to be possible, right? Like with a pen and paper, well, I would say, I mean, I would never be able to figure, I would never guess that would happen, but I guess a lot of these guys did figure this would happen before they could even experiment with it. Like, that's wild. Feynman has a lecture on this.
Experimental observation or any other kind of observation on scientific things. It's intuition.
Particles are manifestations of waves. I think the current understanding of quantum... Well, yeah, so technically everything can exhibit... I believe all matter exhibits wave-particle duality is what we believe now, right? What do you think a single particle is? I think that's the issue. Sure, so I guess like the classical understanding is a particle is an actual thing, but I think in quantum field theory, the idea is that everything is just excitations of fields that are represented with wave functions that is a superposition of whatever the underlying functions are that we can't know until we measure it, I guess. Or maybe don't exist until a measurement is forced. Not a conscious observer, but some type of interaction with another particle happens.
Which is really based on just experience with everyday objects that suggest reasonable explanations for things. But as we try to widen and make more consistent our description of what we see, as it gets wider and wider...
No, it's not causing a diffraction pattern with just itself. Oh, wait.
We want to actually do this experiment because we're so...
Fuck. We're opening too many videos. We would never get through this today.
So awesome at Hitachi Research Labs. Let's do it. So here's what they did. And I'm going to turn off the lights. Great. Okay, and I set this to some music because I like it. Okay, here's what's happening. One at a time, individual photons. Ooh.
Oh, look at how excited this guy is to teach physics. Look at how cute that is.
So they look pretty localized. There's not a whole lot of structure. And now they're going to start speeding it up. This is 100 times the actual speed.
Yeah. Do you know the fact that if you turn on a detector at the slit, the interference goes away? Yes, but I think the explanation for that is that some of the information is picked up by whatever matter measured the photon going through, and so both of those things contain the information. And then if there's another way that you can measure again, you can eliminate that information, and then the interference pattern comes back. But I don't fully understand that. That's the best explanation I can give for that.
Eh? Yeah. So those guys know.
Oh, okay, so you're just confused on the single electron diffraction. I guess, yeah, I don't know why it happens. Who's it interacting with? Why is it diffracting on its own? It's kind of wild.
Eh? Yeah.
That's crazy. Collapsing the wave function, I guess, is the term there. Yeah, but what does it mean? I can say that. What does it mean, collapsing the wave function?
So those guys know what they're doing. Let's see. There we go. So I don't know of a more vivid example of electron interference in that one. It's totally obvious. You see individual electrons. They run through the apparatus. You wait. They run through the apparatus. You wait. One at a time, single electron, like a baseball being pitched through two slits.
Yep.
And what you see is an interference effect. But you
How? What's it interfering with?
don't see the interference effect like you do from light, from waves on the sea. You see the interference effect by looking at the cumulative stacking up of all the electrons as they hit. Look at where all the electrons hit one at a time.
What the fuck?
So is an electron behaving like a wave in a pond? No. No, does a wave in a pond hit at a spot? No, it's a distributed beast. Okay, yes, it interferes, but it's not localized. Well, is it behaving like a baseball? Well, it's localized. But when I look at a whole bunch of electrons, they do that. They seem to interfere, but there's only one electron going through at a time. So in some sense, it's interfering with itself. How does that work? Is an electron a wave? Does an electron hit at many spots at once?
No.
No. So is an electron a wave? No. Is an electron a baseball?
No.
It's an electron.
Wow.
Okay? So this is something you're going to have to deal with, that every once in a while we have these wonderful moments where it's useful to think about an electron as behaving in a wave-like sense. Sometimes it's useful to think about it as behaving in a particle-like sense. But it is not a particle like you normally conceive of a baseball. And it is not a wave like you normally conceive of a wave on the surface of a pond. It's an electron. Let's see if we get,
Dustin, you're not explaining your problem correct. In your mind, the slit is electron size, but what people are trying to tell you is that the electron wave is bigger than the slit? What? In order for this to work, I think the slit has to be larger than the, I think it's just the, is it the frequency? No, it's the amplitude, right, of the wave. So for the double slit experiment, it's arbitrary. It's easy to create one big enough. But like for matter, obviously, it's very, very difficult. What's the largest thing they've shot through? Was it a buckyball? Is that like 60 carbon atoms or something? I think it's the largest thing they've done a double slit experiment on. Is C60, is that what that is? Buckminster fullerene. I feel like it's been referred to as buckyballs before, right? Or am I making that up?
Yeah, so I like to think about this like an elephant. If you're closing your eyes and you walk up to an elephant, you might think like, I've got a snake and I've got a tree trunk and there's a fan over here. And you wouldn't know, like maybe it's a wave, maybe it's a particle, I can't really tell. But if you could just see the thing the way it is, not through the preconceived sort of notions you have.
The wave function spreads out. When a single photon approaches the double slits, it's a wave function, which represents all of the possible paths and states it could take. It spreads out and it goes through both slits simultaneously. This isn't just a classical wave splitting. It's a quantum superposition where the photon exists in a combination of went through left slit and went through right slit states. Easy. Oh, obviously. Wait, actually, hold on, wait. Maybe that actually makes so much sense. I'm reading that like an asshole. But, wait. Is that why, hold on, wait, I think you just made something click. Is that why if you do the double slit experiment, but you measure here or block here or something, that you create only a single slit diffraction pattern? Because the wave function collapses at a measurement here, and then the only superposition that can emit comes from here. Okay, that kind of makes more sense. I say makes more sense as much as, okay. When a single proton approaches double slits, it's a wave function, which represents all the possible paths it could take. It spreads out and goes through both slits simultaneously because it hasn't collapsed yet. And then whenever it hits something or measures, and then so what? So like when people talk about, obviously again, this is like way above, but when people talk about like many worlds interpretation, the many worlds thing is basically just saying that superposition, all of the underlying, like when a measurement happens, every single measurement is correct. It's just happening in different like universes basically. Which is why it interferes with itself, because all of them are happening simultaneously as the waveform propagates. I guess I just have a hard time intuitively understanding why it causes an interference pattern with itself. Because like what I'm trying to figure out is what's actually happening under there, right? So because what's actually happening under there in the wave function. But I guess this is like one of the underlying questions, I guess, in quantum mechanics, huh? Is like, is anything real, or is the wave function actually like reality? Because in my imagination would be that if the wave function is just a probabilistic way of trying to estimate what is like deterministically true underneath, you wouldn't get an interference pattern. Because while we can probabilistically represent where the electron is, in real life it's only in one place. But the measurements that we're taking seem to make it seem like it actually is in all places until it's measured, and then it... That's kind of wild though, no? The wave function is real. Do you know what the dot is? Isn't the dot just a single measurement of a probabilistic place? Yes, but like, so here's the unintuitive part, I think. Okay, don't write these answers on any physics test, okay? This is the unintuitive part, okay? Is if we were to shoot something here, if we were to shoot a beam of light here, and it were to emit out here, right? In either way, right? All these electrons, I can't draw for shit. I don't even know why the fuck I'm trying, right? And then we get these like interference patterns, right? Let's say that we shoot a single electron, okay? If we were to shoot a single electron through here, we would represent it with, we'd call it, I guess, a wave function, right? Well, probabilistic could be anywhere, right? But in our minds, we would think, in reality, it's only in one place, right? It's only in one place. It must be, right? It has to exist somewhere. However, it seems to interact with itself in a way that would imply that it actually is in all places, because when it finally hits this board back here, it's causing an interference pattern such that it seems to be interacting with itself, even if you just fire a single electron, which makes it seem like it doesn't exist until it's actually measured. And prior to that, the wave function is reality, I guess. That's like it seems to be the weird thing. So like, imagine it's like bumper cars. Like if you were to send a whole stream of bumper cars into here, imagine that by the end, all of the bumper cars are fucked up. And it's obvious why they're fucked up. It's because they're all hitting each other, right? So all the bumper cars are going through here, and the bumper cars are smashing into each other, and they all come out with very predictable, bumper fuck-ups and scuffs and everything. And you're like, okay. And let's say you want to know at any one point in time, like, well, where the fuck is a particular bumper car? And you'd look in here, and you could freeze and stop, and then look. It's like, okay, I see where all the bumper cars are. I see how they're hitting each other. I see, like, the type of, where we say there's, like, collisions. We might call this, like, destructive interference. We can see where the bumper cars are hitting each other. And then you play it again, and they all go, and they come out here with all these, like, fuck-ups. And you're like, okay, well, hold on. I'm curious. I want to send my friend. This is the mindfucky part. I'm going to send my friend through with one bumper car on his own. Now, where is my friend at any point in time? Well, I don't know. All the bumper cars could hit each other. Now, so I represent this probabilistically. He could be anywhere here, right? And then let's say we measure at the end, and we're like, okay, well, where's my friend actually? Okay, well, here he is. And then your friend comes out, but your friend's car is fucked up. And you're like, how the fuck is your car fucked up? You came through on your own. You were a single electron. You're just one bumper car. And it's like, well, I mean, I wasn't just here. I was actually in all the spots probabilistically that you would expect me and all the other bumper cars to be. It's like, no, you can't possibly be that. You're just yourself. You're just your own bumper car. How are you colliding with yourself such that you're causing a diffraction pattern? You're interfering with yourself. And that's like the weird thing. I don't understand. That's just wild. That just seems kind of crazy. I'm not sure this analogy works at all with a single electron. I think it does. Because that's why it's weird. Do waves in a pond appear weird when they interfere with themselves? No, I don't think but the problem is that waves in a pond, like that wave thing, that's just a wave. I don't think that we see that as like a single piece of matter, like they propagate as waves, right? Because the concept of a single electron doesn't exist. Okay, you say that, but if we shoot a single electron through, one electron, when we measure back here, we don't measure a wave function, we measure a discrete singular electron hitting the sheet. Okay. Stop. Okay, we'll watch this guy talk about it, and then we'll move on from this. Sorry. I thought it was kind of crazy when I wikied this. Late at night in my dreams.
As a 42-year-old who's spent most of my life studying physics, I must admit that I had a big misconception. I believed that every object has one single trajectory through space, one single path. But in this video, I will prove to you that this is not the case. Everything is actually exploring all possible paths all at once. So let's start with a simple thought experiment. Say you're at a beach when all of a sudden you see your friends struggle.
Hold on, I'm so sorry. I just want to say this because I think this is wrong, but I understand why you're saying it. But I used to think this up until yesterday, okay? But I might be incorrect, okay? But because I've heard like some of these like shortcuts for understanding. So somebody says, measuring causes the collapse. In order to see something, you have to touch it. We just don't think about it like that. Even turning a light on bounces photons off of something. So that's what I thought, okay? I thought. Now, I'm not going to give a high degree of confidence to this because obviously I don't know much, but I'm like, oh, well, wave functions and wondering about whether or not things actually exist or if there's a discrete reality, this seems kind of retarded. Like, obviously, the electron is somewhere and the wave function is just approximating that. And then when you see something, you figure out where the thing actually is. But it's not that simple. The issue is that it's not that when you see something, you cause it to take a finite position. It's that prior to that, like it truly does act like it's in all positions such that it is causing an interference pattern with itself, with a singular electron. A single particle will interfere with itself in a way that you would only imagine a whole group of things could, like a wave could. And a single particle can't be a wave, right? You would imagine. So I understand what you're saying there, but it's not just like when you see something, you force some kind of like wave function to collapse. Is that prior to the collapse of that wave function, it almost seems like the wave function, the approximation of reality is real, that the wave function is a real thing, that the probabilistic distribution of a thing in space that's real. That's like as real as it gets, that there is no underlying discrete reality about where a thing is. But that seems like that seems kind of, I don't know, that seems like kind of weird, but okay.
Experiment. Say you're at a beach when all of a sudden you see your friend struggling out in the water. You want to go help him as quickly as possible, so which path should you take to get there? The shortest path is a straight line, so you could head directly towards him, but you can run faster than you can swim, and this path requires more swimming. So alternatively, you could run down the beach to minimize the distance through the water. But now the total distance is longer than it needs to be. So the optimal path, it turns out, is somewhere in between. To be precise, it depends on the speeds at which you can run and swim. Now, you might recognize this mathematical relationship because it is the exact same law that governs light passing from one medium into another.
Cringe.
So light...
Try to solve this before he says the answer? Wait, were we already supposed to guess? Wait, let me listen again. I'm sorry, I was reading chat for this. Sorry, one sec.
This is not the case. Everything is actually exploring all possible paths all at once. So let's start with a simple thought experiment. Say you're at a beach when all of a sudden you see your friend struggling out in the water. You want to go help him as quickly as possible.
There was nothing to solve? Oh, well.
Which path should you take to get there? The shortest path is a straight line, so you could head directly towards him, but you can run faster than you can swim, and this path requires more swimming. So alternatively, you could run down the beach to minimize the distance through the water. But now the total distance is longer than it needs to be.
Oh, how do you balance this out? Oh, I don't know, the equation or whatever it is for this. Sorry. Okay.
So the optimal path, it turns out, is somewhere in between. To be precise, it depends on the speeds at which you can run and swim. Now, you might recognize this mathematical relationship because it is the exact same law that governs light passing from one medium...
That one. I would just do that. I would think sine... I don't remember what the symbol is. Over that, but I would... Theta. Yeah, I would calculate all that in my head instantaneously.
...into another. So light also takes the fastest path from point A to point B. What's weird about this is that as humans, we can see where we want to go and then figure out the fastest route. But light? I mean, how does light know how to travel to minimize its journey time? Now, here is where my misconception comes in. I shine a laser beam. The light just goes in one direction. I throw a ball. The ball just goes in one direction. You know, I would have answered, there is nothing strange about this. Light sets off from point A in some direction, and then a little while later, it encounters a new medium. And due to local interactions with that medium, it changes direction, ending up at point B. If you later find that of all the possible paths, light took the shortest time to get from A to B, I wouldn't think it was optimizing for anything. I would just think that's what happens when light obeys local rules. But now I will prove to you that light doesn't set out in only one direction. Instead, it really does explore all possible paths. And the same is true for electrons and protons, all quantum particles. So the fact that we see things on single, well-defined trajectories is, in a way, the most convincing illusion nature has ever devised. And the way it works all comes down to a quantity known as the action.
Whoa!
In a previous video,
Is this gonna have anything to do with what we were just talking about, or?
we showed how an obscure scientist, Maupertuis, made an ad hoc proposal that there should be a quantity called action, which he defined as mass times velocity times distance. And he claimed that everything always follows the path that minimizes the action. Hamilton later showed that this action is equivalent to the integral over time of kinetic
Back when we had smart presidents.
energy minus potential energy. Action was useful and an alternative way of solving physics problems, especially when Newton's laws get too cumbersome. But then, around the turn of the 20th century, action showed up at the heart of a scientific revolution.
Whoa!
The birth of quantum mechanics.
Oppenheimer!
It all started with electric lighting in Germany.
Think about what it's like in the 1890s, right? Electricity being more widely available, at least in urban centers, and things like, light bulbs. They were new. They were literally the hot new thing.
Germany wanted to replace all their gas streetlights with electric light bulbs. So an important question was, how do you maximize the visible light given off by a hot filament? Scientists at a German research institute, the PTR, studied how much light different materials emitted as a function of temperature. At low temperatures, each material gave off its own characteristic spectrum, mostly in the infrared. But above about 500 degrees Celsius, all materials started to glow in the same way, with an almost identical distribution of light. The hotter the object, the more energy was emitted at every wavelength.
This is why your mom emits all the light, because she's so fucking hot.
And the peak of the distribution shifted to the left.
But they still didn't understand.
200 years ago, you could literally know everything. Yeah, that's why it's so annoying. You go to like the 1700s and there's all these people who are like polymaths, right? This guy knows so much about everything. And it's like this guy figured out 2 + 2 = 4, and now he can contribute to like 17 different fields of science. Like, motherfucker, give me a break, okay? Like, your math class goes up to like math 2. You learn like algebra, like the basics, like I know what a variable is, and now if I like draw 3 more letters on my piece of paper, I've furthered mathematics and basically through parallel exploration like 20 other fields. Okay, fuck you, all right? Fuck those people.
And the peak of the distribution shifted to the left.
But they still didn't understand how it
More like algebra.
worked theoretically. So that was sort of the next step, right? Because if you can understand how it works theoretically, then you can use that theory to potentially design new products.
They started by imagining the simplest object possible, one that would absorb all light that falls onto it and perfectly emit radiation based on its temperature. They came up with a hole in a metal cube. This hole is a perfect blackbody because any light that shines onto it will go straight in.
One potential answer is to just assume there's a hidden RNG seed and code it into the universe from the beginning, and that everything in the universe that computes uses this seed, hidden variable. So everything is essentially pre-correlated. It's fundamentally untestable as far as I know, but it's a nice loophole. But that still wouldn't explain single electron diffraction patterns. The thing that it seems kind of wacky is that, like, let's say that I'm spying on my downstairs neighbor. Okay, I've got hidden audio camera machine. I can see exactly, and through the course of the day, I know that they spend 50% of their time in the kitchen, and I know they spend 50% of their time in their bedroom. Okay. Now let's say that somebody were to ask me, hey, where is the person? Now I would say, let's say that I'm not currently looking at my equipment, and let's say the time is random. Now I can say, well, there's a 50% chance that they're in the kitchen, there's a 50% chance in their bedroom, right? Now, in reality, we know that they are in one place or the other. But it seems like when it comes to like wave function stuff, this is as real as it gets. Somebody says, where? Oh shit, this is what I just understood this is what the Schrodinger's cat thing is, isn't it? The answer though isn't that, see, now when I'm thinking of the Schrodinger's cat thing, my thought I guess was that when you measure if the cat is alive or dead, then you figure out if it was alive or dead. But that's not actually what you're figuring out. You're forcing a discrete measurement, but prior to that, I don't even know why they call it a superposition, because I feel like a superposition implies, doesn't superposition mean like two other like linear discrete waves that are being added or whatever, and the superposition is the like the superposition was the realest thing there was. Like it's called a superposition, but it's not like there's an underlying reality that gives way to some probability and then we can only measure the probability. It's that the probability is the realest thing there is. So when somebody asks like, where's the person? And it's like, well, do you want to look? And they're like, I don't want to look. And it's like, they're 50% in the kitchen and 50% in the bedroom. It's like, well, yeah, but it must be one or the other. Let's guess. No. The correct guess is this. They don't exist in one place or another. The superposition is the realest form of existence. This is the realest actual measurement of reality that exists. It's not until we do some kind of discrete observation that they will be forced to take, I guess, a particle posture and be in one spot, which seems kind of weird.
Bounce around inside and eventually be absorbed. But this also makes it...
When I think of the Schrodinger's cat thing, my assumption was just that, well, we can't know. My assumption for Schrodinger's cat was like, you give a cat a pill and it's either a 50% poison pill, 50% water, and then you put it in a box and it's like, well, we don't know. It's in a superposition of alive or dead until we open the box and see. But that's not the case. What the case is that it is both alive and dead until you open the box and then you force it to assume a discrete thing. I don't know. That's just really weird to me. That's just kind of crazy. Okay.
Light that shines onto it will go straight in.
No, wait. Yeah, so with this person, but they're actually somewhere. No. That's the thing. I don't think they're anywhere. They're just the wave function. They exist in a probabilistic scattering of things, but there's not like an underlying reality that we're trying to probabilistically explain with a wave function. It is what it is. It seems to be the case.
Bounce around inside and eventually be absorbed. But this also makes it a perfect emitter. Any radiation inside the cube can escape through...
Einstein didn't believe that, by the way. Well, Einstein was a loser who didn't like quantum mechanics, so we don't care what he thinks.
The perfect blackbody, because any light that shines onto it will go straight in, bounce around inside, and eventually be absorbed. But this also makes it a perfect emitter. Any radiation inside the cube can escape through the hole unimpeded. Theorists reasoned that electrons in the walls of the cube would wiggle around emitting electromagnetic waves. These waves would then bounce off the other walls. When you have two waves of the same frequency, where one travels to the right and the other to the left, they can interfere in such a way that they create places where there's no wave amplitude, those are nodes, and places where there's maximum wave amplitude, the antinodes. Waves like this are called standing waves because they don't really move left or right. And inside a cavity, given enough time and reflections, it is only these standing waves that survive. All the other ones just cancel out. So a sort of order emerges from the chaos. In 2 dimensions, standing waves look something like this. For shorter wavelengths or higher frequencies, you can fit more and more different vibrational modes.
Wait, fuck, did he explain that more? And I was reading chat. I feel like the understanding of like how waves interact with each other and what does coherence mean? If something is coherent, does that mean that it increases the amplitude, or if they're constructive or destructive? The interference or whatever, like having them like average out to be like nothing or having them increase each other. I feel like that's an important concept. I didn't realize how that, I guess, related to the cringe stuff here, but.
This. For shorter wavelengths or higher frequencies, you can fit more and more different vibrational modes inside this cube. So that in 3 dimensions, the total number of modes is proportional to frequency cubed, or 1 over lambda cubed. The expectation was there would be more and more waves inside the cube the shorter the wavelength.
Remember a while ago I said that, I don't know if I was talking about camera stuff or whatever, but like because I said signal theory seems very interesting. I feel like the little graph things with all the waves, this shit is like everywhere. There's like a lot of parts of reality I feel that are governed by by signals on graph. There's a lot, it's like a lot of shit. There's a lot, it like impacts like fucking everything, but.
This led directly to the Rayleigh-Jeans law. At longer wavelengths, it matched the experimental data pretty well. But at shorter wavelengths, the theory diverged from experiment. In fact, it predicted that at the shortest wavelengths, an infinite amount of energy would be emitted. This, for obvious reasons, became known as the ultraviolet catastrophe. The person to solve this problem was Max Planck.
But Planck almost didn't make it into studying physics. Because when he was 16 years old, he went up to his professor and asked him, well, maybe I could do a career in physics. To which his professor responded that he'd better find another field to do research in, because physics was essentially a complete science. You know,
a physics professor I had told me that most of the math done in higher levels of physics is a derivation of basic spring and wave mechanics. Fuck, I read this quote yesterday. Well, I don't even know the math or the physics involved, so I can't even remember the quote. But it was something that, like, I'm not even going to know it. Spring and harmony and something, and like all of things are basically this. What is the, does anyone know this quote? Is it a physics quote? Oh, I found it. I don't know what this means though. I'm such a good Googler. Any kind of attractive interaction potential is approximately simple harmonic near its equilibrium point. There you go. I don't actually know what basically any part of that means. Attractive interaction potential. I don't know what that means. Simple harmonic. I know what harmonics from music are. I don't know if that relates there. Near its equilibrium point. I know what an equilibrium is. That's when I have just enough cum and dick in your mom that if I pull my dick out, there'll be an empty space. And if I push my dick in, cum will come splurging out of her.
there was just a few tiny little problems that they had to clean up. But besides that, it was over.
But Planck didn't listen. By 1897, he was a professor himself, and for the next 3 years, he struggled to find a theoretical explanation for blackbody radiation. He tried approach after approach, but no matter what he tried, nothing worked. He said, "I was ready to sacrifice every one of my previous convictions about physical laws." Then, in a, quote, act of desperation, he did something no one had thought to try. According to classical physics, the energy of an electromagnetic wave depends only on its amplitude, not its wavelength or frequency. And it could take any arbitrary value. So any atom could emit any wavelength of light with an arbitrarily small amount of energy. But Planck tried restricting the energy so that it could only come in multiples of a smallest amount.
Wait, I don't want to spam, but I just want to clarify this. There are empirically indistinguishable theories of QM that have classical particles traveling along well-defined trajectories. The quantum physical effects come from the fact that the guidance equation that gives the dynamics of the particles is derived from the wave function. At least in non-relativistic QM, this works very nicely. It is not a Lorentz invariant, though, and struggles with generalizations to QFT. Oh, of course. I mean, obviously. Obviously we knew that, right? I learned that when I was learning how to write. What is it called? There's a single equation, I think, that's supposed to represent like the classical model of physics. Is that called the Lorentz variant? Or what is it called? What is the name of this equation? It's retardedly. Oh, Lagrangian, I think is what I'm thinking of. Is it what I'm thinking of? Oh. This is the standard model Lagrangian. It's an equation that encapsulates everything that we currently know about particle physics. There it is. In its most simplified form. Easy. How much of this can someone understand if they only had a bachelor's in physics? I have a bachelor's in particle physics. I get a bachelor's in particle physics. So I understand is that it's just demonstrating the state of the standard model, and I know most of the symbols and can figure out some of the interactions that are occurring between the particles, but honestly, looking at it shows how little I understand about particle physics. Yes, now I understand. Based, okay.
Quantum. And he made the energy of one quantum directly proportional to its frequency, E equals hf, where h is just a constant. Think about what this does to the...
Sorry, hold on. I just want to destroy this. I'm sorry, because there's a couple things when people talk about quantum mechanics that's super retarded. One has to do with like quantum entanglement doing faster than light travel, which is, we've done that. But another one is, I believe that when you talk about an observation in physics, I'm responding to this question. If we extrapolate to existence as a whole, does this mean that we're only what we are because of what people perceive us to be? Do we even have any sort of agency if we exist in all aspects of reality at all times? We only materialize in people perceive. When people talk about measurements in physics, you're talking about some sort of like particle interaction or some sort of measurement. It's not like a conscious being observing things. Like sometimes people use measurement, or they'll reference the double-slit experiment. They're like, oh, well, when a human being observes something, that's when reality materializes. It has nothing to do with a human being observing a thing, and it just has to do with like particle interactions that force things to take like a discrete like measurement or whatever. It's not okay. Just saying that, because some people think that it's like conscious beings force wave state classes. Is not true.
And he made the energy of one quantum directly proportional to its frequency.
Somebody said, I don't know what is happening in this video. This is easy. Some dude was trying to get stuff to show the same color light, and then this guy went to school when he was 16, and his professor tried to molest him, and he was like, in an act of desperation, I need to save myself by reinventing all of physics, and then he looked at quantum excitations of particles. Dipshit.
E equals hf, where h is just a constant. Think about what this does to the radiation coming from the black body. At a given temperature, the atoms in the cavity have a range of energies. Some have a little bit, a few have a lot, and most have their energy somewhere in between. For long wavelength, low frequency radiation, the energy hf of one quantum is small, so all of the atoms have enough energy to emit this wavelength, and the spectrum matches the Rayleigh-Jeans prediction very well. But at shorter wavelengths, higher frequencies, the energy of a quantum increases. And now, not all of the atoms have enough energy to emit that wavelength. This is why experiment diverges from the classical prediction. The spectrum peaks and then starts to fall, because fewer and fewer atoms have enough energy to emit one quantum of that radiation.
Wow.
And there comes a point when none of the atoms have enough energy to emit one quantum. So here, the spectrum must drop to zero. With this approach, Planck got a new formula for the radiation spectrum. Now, all that was left for him to do was to tune the parameter h, and when he did this just right, he got his formula to match up perfectly with experiment.
But he was sort of troubled by his own formula, because to him it was just a mathematical trick. He had no clue why it worked. It was purely formal. And most importantly, he had no clue what this h represented. I mean, he had introduced a new physical constant without any reason.
He wrote, a theoretical interpretation had to be found at any cost, no matter how high. So from
the cost is just him sitting inside all day like a fucking loser, scribbling on a piece of paper.
That moment on, he dedicated himself to finding one. He later reflected that after some weeks of the most strenuous work of my life, light came into the darkness, and a new, undreamed-of perspective opened up before me.
He introduces what we now call Planck's constant.
Holy shit, Prof G used to do physics? Oh, applied mathematics, never mind.
And it has the units of action. Planck's constant h is a quantum of action.
Planck later proposed that anytime any change happened in nature, it would be some whole multiple of this quantum of action.
So it's kind of spooky, this breakthrough that starts the ball rolling toward quantum theory, brings action in.
Wait, I think Destiny's mixing waves and quantum mechanics with waves in a lake. Waves are math, that's the thing in common. But I think that's the whole thing that a single electron double split experiment shows, is that a single electron will act like waves in a lake. That's the mindfucky thing. I think that's why it's so fucking weird.
Not energy and not force, action. Gives you a hint.
At first, the quantum of action got little attention. That is,
time guesser. Sorry.
Till a 26-year-old patent clerk came on the scene. In 1905, Albert Einstein claimed that Planck's theory wasn't just a mathematical trick. It was telling us that light actually comes in discrete packets, or photons, each with an energy hf.
Whoa.
Einstein used this insight to explain the photoelectric effect, how light can eject electrons from metal.
Wave functions are in configuration space, not in physical space. Yeah, I think that's true, but that is for mathematical reasons that are beyond me. It's something like you only want to work with linear and not nonlinear equations, so you can have Hilbert space or something. But I don't understand any of that. That's too much for me. Don't care.
But only when the frequency is high enough. If the frequency is too low, no electrons will be emitted, regardless of the intensity. The idea of quantization spread. 8 years later, Niels Bohr was trying to understand how an atom is stable if it has a positive charge in the center and negative electrons whizzing around it. Why don't they just spiral into the nucleus, radiating their energy as they go?
And what he wants to do is, he says there's something fishy about something being discrete. That seems to be the new ambiguous weirdo lesson of the new quantum of action.
Bohr realizes that as the electron goes around the nucleus, it has an angular momentum. Mass times velocity times radius. So angular momentum has the same units as action.
And so what he decides to do is discretize the orbital angular momentum for no good reason. He says, let me slap that on and say angular momentum of the electron can only be in 1 unit, 2 units, 3 units of the same quantity h. And because it's talking about motion in a circle, the factors 2 pi come in, so it's really nh over 2 pi, what we now call nh bar.
Wow.
This comes out of nowhere. There seems like absolutely no good reason why angular momentum should be quantized. But by doing it, Bohr finds the correct energy levels of the hydrogen atom. When an electron jumps from a higher orbit to a lower one, the energy difference is given off as a photon of a particular color of light, exactly reproducing the hydrogen spectrum.
And that was a pretty startling thing to have fall out. I think that really was compelling. It takes some quantity with units of action and apply some, again, kind of ad hoc just discretization and quantization to it.
Now, although it worked spectacularly well, no one could make sense of it. That is, until 11 years later. For his PhD, Louis de Broglie was contemplating the recent discoveries in physics, and his big insight was that if light could be both a wave and a particle, then maybe matter particles could also be waves. He proposed that everything, electrons, basketballs, people, absolutely everything has a wavelength. And he defined this wavelength analogously to light, as Planck's constant divided by the particle's momentum, or mass times velocity. Now, if an electron is a wave, the only way it could stay bound to a nucleus in an atom...
Yeah, I feel like there's a dumb... There's a thing that people that are very good at a thing do that I think is misleading to people that aren't good at a thing. Like when he said here, he took this, idea for no reason and did this thing. I don't understand all the underlying math here, but it probably wasn't for no good reason. I'm sure the guy has a ton of mathematical and physics intuitions built up. It's like when somebody's really good at like a game or like music or whatever, and like, oh, I don't know, I thought these two things would sound good together, and I just randomly tried them together, and it actually sounds really good. But when they say randomly try together, you're thinking like random, so I could like make that thing. Well, my random stuff doesn't sound good. Why not? And it's like, well, when I say random, I mean, I'm in a functional harmony space doing some modal alignment with blah, 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 blah. And then I try, and it's like, okay, you're so much more structured. When you say random, you mean something that's so much different than when I heard random, Yeah.
Now, if an electron is a wave, the only way it could stay bound to a nucleus in an atom is if it exists as a standing wave. That requires that a whole number of wavelengths fit around the circumference of the orbit. You could have 1 wavelength, or 2 wavelengths, or 3, and so on. So the circumference 2 pi r must be equal to some multiple n times the wavelength. We can sub in de Broglie's expression for the wavelength to get that 2 pi r equals nh over mv. But we can rearrange this to get that mvr, the angular momentum, is equal to nh over 2 pi. That is precisely Bohr's quantized angular momentum condition. But now we have a good physical reason why it's quantized, because electrons are waves, and they must exist as standing waves to be bound in atoms.
Because they want to have constructive interference of a stable orbit back. That's pretty good. You get a dissertation out of that. That's pretty good.
It is this wave nature of quantum objects that means they no longer have a single path through space. Instead, they must explore all possible paths. Now, I have thought about and taught the double-slit experiment hundreds of times without fully realizing this implication. In the double-slit experiment, I feel like the mental thing that I'm doing in my head is like, okay, well, the beam is not perfectly straight, and of course it's going to intersect both of those slits, because they're really close together, But then I heard this story about a professor teaching the double-slit experiment, and it makes everything so clear.
Oh my God.
So the professor...
I heard a story about a professor teaching... Okay.
Starts by explaining the setup. Electrons are fired one at a time through 2 slits to be detected at a screen. Now, because you can't say for certain which slit the particle went through, quantum mechanics tells us it must go through both at the same time. So to get the probability of finding a particle somewhere on the screen, you simply add up the amplitude of the wave going through one slit with the amplitude of the wave going through the other slit and square it. But that's when a student raised his hand. What if you add a 3rd slit?
What?
Just add up the amplitudes.
Okay, wait. So this was the thing that I thought was mind-blowing. I feel like everybody skips over this. Or maybe everybody understands this but me. I don't know.
Going through the other slit.
That's my assumption prior to yesterday. My assumption was that it exists for real somewhere, right? So it's going to act like a single thing going through somewhere. But it doesn't. It truly is in all places such that this interference pattern, right? This is an interference pattern, meaning that as it propagates as a wave and then it interacts with the other wave, there are different points in space where it's going to cause constructive and destructive interference, right? But this interference pattern exists even with a single electron. Even when you fire that's something when they say fire the electron through one at a time, that interference pattern exists in space up until you take a measurement. So when you start measuring these single electrons, they spread out, creating this diffraction pattern, even though you're just firing them one at a time. That's crazy. That's kind of weird. Well, not kind of, it can't be kind of weird and crazy. It's very weird and crazy.
Slit and square it.
What does a third slit do? Why does that even matter? What about a fourth slit? Can I be really smart if I say, what about a fourth slit?
But that's when a student raised his hand. What if you add a third slit? Well, you just add up the amplitude.
He drops his chalk. He starts shaking.
Of the waves going through each of the 3 slits, and you can work out the probability. The professor wanted to continue, but then the student interjected again.
What about a fourth one? And then his brain exploded.
What if you add a 4th slit and a 5th? The professor, who is now clearly losing his patience, replies, I think it's clear to the whole class that you just add up the amplitudes from all the slits. It's the same for 6, 7, etc. But
oh, shit! I don't know, actually. He's going to say then the whole universe is like this?
Now the bold student pressed his advantage.
What about the 9th slit?
What if I make it infinite slits? So that the screen disappears. And then I add a 2nd screen with infinite slits, and a 3rd, and a 4th. The student's point was clear.
He's shaking.
Even when we're not doing a double slit experiment, when it's just light or particles traveling through empty space, they must be exploring all possible paths. Because this is exactly how the math would work if you had infinite screens, each with infinite slits. You have to add up the amplitude from each slit. That's just the way it works.
According to the story, the student was Richard Feynman. And
then the professor killed himself after that class.
While the story is made up, the logic is flawless.
Oh, never mind.
Because if you believe in a double slit experiment, that you can't tell which of the 2 slits the particle went through, then you have to consider the possibility that it goes through both. By that same logic, anytime any particle goes from place 1 to place 2, you have to consider all the possible paths it could take to get there, including ones that go faster than the speed of light, including ones that go back in time, and including ones that go to the sun and back.
I feel like it can't go to the sun and back. You have to restrict it to be local, right?
So the math doesn't do that. I mean, you could see that just in the double slit experiment, right? And we'll do light, because then there's no funky business with the speed. If you're going to
Are we seriously deciphering the building blocks of the physical universe while there's an ongoing genocide in Gaza? Well, the whole point about going over this means that there's some universes where maybe there's not an ongoing genocide. And that's why we're watching this, okay?
say like this path interferes with this path, then these distances are different.
Right.
And so clearly they can't have the same speed. So you need to consider paths that have different speeds.
Feynman's way of doing quantum mechanics suggests that anything going from one place to another is connected in every possible way. And the internet is kind of like that too, connecting us to anything anywhere at any time. At least in theory. There are still artificial barriers like geo-blocks and country restrictions that block off parts of the internet. But fortunately, there's today's sponsor, NordVPN, which can help knock down those barriers.
NordVPN?
Just connect to one of their thousands of servers, for example, this one in the US, and it looks as if you're accessing the internet from there. The team and I travel a lot to make these videos, and using a VPN is a game changer. It allows us to access the news sites and articles we need, no matter where in the world we are. And personally, I also love that NordVPN allows me to stay up to date with how the Canucks are doing back in Canada. Not very well at the moment. Canucks have a real shot.
Fuck! Hassan just said genocide is happening in every universe. I didn't know that. God damn it.
This year.
The goddamn Mossad has penetrated all of them.
But to try NordVPN for yourself, sign up at nordvpn.com/veritasium. Click that link in the description or scan this QR code. And when you do, you get a huge discount on a 2-year plan and an additional 4 bonus months for free.
Does this end with the Everett interpretation and Sean Carroll's advocacy? When you get into like actual like QFT and you get into actual interpretations of quantum mechanics, you have to have a very, very, very good understanding and a very high level mathematical understanding. There's no way I would ever even be able to give you anywhere remotely close to an opinion about what is more correct or whatever, because I don't even have close to the intuitive understanding of the underlying fundamental aspects of these theories. So I would never even begin to to estimate. The only thing I would ever say is I would always trust anything Sean Carroll says over any of the Weinstein fuckers. That's it.
It's the best deal, and it also comes with a 30-day money-back guarantee. So head to nordvpn.com/veritasium to try it out risk-free. I want to thank NordVPN for sponsoring this part of the video, and now let's get back to Feynman's crazy way of doing quantum mechanics.
So, according to Feynman, anytime a particle, a photon, or even a macroscopic object moves from point 1 to point 2, it has some chance to take any path. And as preposterous as it might sound, he found that we need to include all these paths in our calculation, where each path is weighted the same.
So why then do we not see all those crazy paths? Well, that's because we still need to add up their amplitudes.
Learn math only through Wikipedia. I've heard that the math sections on Wikipedia are actually all really good. I don't know if that's true or not. Maybe because it's not like as controversial. It's easier for people to just step in and add stuff, but...
For simplicity, imagine we only have 3 paths. Then here's what we're going to do.
Okay.
First, let's take this one. When the particle wave starts following it, we start a stopwatch. It goes around and around.
Wait, Sean Carroll is a bit wacky, to be honest. He is much into that string theory thing. Is he? I thought Sean Carroll says that string theory is kind of wacky and he doesn't give it much credence, but I could be wrong.
Very fast, and when it gets to the end point, we hit stop. We'll do the same for the other 2 paths. And then we add up the arrows.
Wait, fuck. I need to pay attention. Sorry. It's too dumb.
Stop.
Okay.
Here's what we're going to do.
Okay,
First,
what are we gonna do?
Let's take this one.
Okay.
When the particle wave starts following it, we start a stopwatch.
Okay.
It goes around and around very fast.
Okay.
And when it gets to the end point, we hit stop.
Okay.
We'll do the same for the other 2 paths.
Okay.
And then we add up the arrows, square the result, and that is then proportional to the probability the particle took those paths to get there.
Whoa! Wait. Have Yudkowsky on to teach us why many worlds is right. He literally wrote more about it than AI when he first started the rationalist community. Does he have a background in physics, or is this just like a pop sci layman's approach to many worlds? You can link me a thing on it. Link me an essay of his or whatever, but...
In this case, the arrow and square.
Oh, Reason Riffs! You're here, what's up? We generally use the Maths Wiki in my research group when looking up basic concepts. Cute.
Are pretty small, so the probability of the particle going from 1 to 2 using these paths is small. Compare that with these 3 paths, for example. Well, now the arrow is much larger. And this is important. The larger the resulting arrow, the higher the probability of that event happening. Now, in these examples, the stopwatch is not actually measuring time.
Okay, hold on.
The arrow is much...
Okay, I'm not pausing for 5 minutes, sorry. I have to pay attention to this, or I'm not going to sound this long.
First, let's take this one. When the particle wave starts following it, we start a stopwatch. It goes around and around very fast, and when it gets to the end point, we hit stop. We'll do the same for the other 2 paths. And then we add up the arrows, square the result, and that is then proportional to the probability the particle took those paths to get there. In this case, the arrow and square are pretty small, so the probability of the particle going from 1 to 2 using these paths is small. Compare that with these 3 paths, for example. Well, now the arrow is much larger. And this is important. The larger the resulting arrow, the higher the probability of that event happening.
Am I retarded? How does he get the arrows again?
This path and around very one. Imagine we...
Okay,
well,
sorry,
that's because we still need to add up their amplitudes.
For simplicity, imagine we only have 3 paths.
Okay.
Then here's what we're going to do.
Okay.
First, let's take this one.
Okay.
When the particle wave starts following it, we start a stopwatch. It goes around and around very fast, and when it gets to the end point, we hit stop.
Okay.
We'll do the same for the other 2 paths. And then we add up the arrows, square the result, and that is then proportional to the probability the particle took those paths to get there. In this case, the arrow and square are pretty small, so the probability of the particle going from 1 to 2 using these paths is small. Compare that with these 3 paths, for example. Well, now the arrow is much larger.
Oh.
And
because they're adding them as vectors or whatever, and that's okay, and that's why we're okay.
This is important. The larger the resulting arrow, the higher the probability of that event happening.
Wow!
Now, in these examples, the stopwatch is not actually measuring time. Instead, it measures something called the phase.
Whoa!
Just as in the double-slit experiment, when a wave takes a different path from point 1 to 2, it will end up there with a different phase. And this phase is what determines the amplitude of the wave at that point. Mathematically, we can write the amplitude, our stopwatch, as e to the I phi, where phi is the phase. As the particle wave follows a path, its phase increases, winding the vector around. So now the big question is, how much does the phase change for each path? Well, to answer that, imagine we split up the path into many tiny sections, each one so small that it's effectively straight.
Okay.
Then, in each section, the particle wave goes a distance delta x in a time delta t, and the increase in phase is easy to compute. It just depends on the wavelength and frequency of the wave. To find the total increase in phase for the whole path, we just add up all the little phase increases of all the individual sections. But we can sub in lambda equals h over mv from de Broglie, and using E equals hf, we can sub in for frequency. We can also simplify by writing h over 2 pi as h bar to get this expression. Then we can take delta t to the
okay.
right. And if we make delta t infinitesimally small, then we
of course.
can replace this sum with an integral. But now dx by dt is just velocity, so we can write this as mv squared.
Oh, of course,
Now, we know that in the simplest case, the total energy E is just kinetic plus potential energy. And subbing that in, we're left with the integral over time of kinetic energy minus potential energy.
Of course.
But wait a second, that is just the classical action. So it's action that determines how fast the stopwatch turns. As the particle moves along a trajectory, its action increases, and that is what increases the phase. And what's important to note is that h bar is tiny. It's about 10 to the minus 34 joule seconds, which is way smaller than the action of any everyday object. That means the phase of ordinary objects on ordinary paths spins around zillions of times, eventually pointing in some random direction. If you consider a slightly different path, the action may be slightly different, say 0.01 joule seconds different. That doesn't seem like much, but divide it by h bar, and the arrow will spin around 10 to the 32 more times. So again, it will just point in some random direction. This is what happens to almost all of the possible paths. So when you add up the phases, they just cancel out. They destructively interfere.
The only exception is for the paths closest to the path of least action, because these paths are at a minimum. So if you make tiny changes to the path to first order, the action doesn't change.
And so for other paths that are very close to the path of least action, their arrows point in basically the same direction. They constructively interfere, and that is why those are the paths we see.
This explains how light knows where to go. I mean, it doesn't. It just explores all possible paths. But the paths we end up seeing are the ones that interfere constructively. And those are the paths of least action.
Oh, of course.
So really, this is how classical mechanics emerges from quantum mechanics. It's why a ball follows the trajectory it does, and how planets orbit the sun. They don't really have a precise trajectory. Instead, everything explores all possible paths. It's just that massive particles have large actions compared to h bar, so that only paths extremely close to the true path of least action survive, which is why they're much more particle-like. If you go to much smaller particles like electrons or photons, the actions are much smaller, and so there's more of a spread in which trajectories they actually end up taking. Now, you might say, I still don't believe you, but Casper has this incredible demo. Now,
I think he said something I almost kind of understood there. Hold on.
Explores all possible paths. It's just that massive particles have large actions compared to h bar, so that only paths extremely close to the true path of least action survive, which is why they're much more particle-like. If you go to much smaller particles like electrons or photons, the actions are much smaller, and so there's more of a spread in which trajectories they actually end up taking. Now,
of course.
Now, you might say, I still don't believe you, but Casper has this incredible demo that should convince you 100% that this is really how the world works.
Finally, a demo.
To do it, I've got a light, a mirror, and a camera. Now, there are infinitely many paths that the light could take. And according to Feynman, we have to add up the contributions of each of them, including paths that go like this. Now, you might say he's crazy.
I'm not crazy. That's what happened.
He's not
Another
crazy.
possibility is it could come here and go. Or it could come here and go. Or it could come where you'd like it to come and go. And it can go over here and go, and so on, and so on. And these are all possibilities.
Why does he talk like this? Why not talk normal? Loser.
Every single one of these paths has their own little arrows. So what we can do is we can look at all those arrows and see where they line up. And so if I turn on this light, that's exactly where you see it reflect, so that the angle of incidence is equal to the angle of reflection. But now what I'm going to do is I'm going to cover up that spot so that we no longer see the light reflect. And then I'm going to prove that Feynman is right, that really light also goes like this. It's just that most of the time, those effects are canceled out. Now, that sounds impossible, right? But it's just that, but now what I'm going to do is where you see it reflects all those arrows and see where they line up. And so if I turn on this light, that's exactly where you see it reflect, so that the angle of incidence is equal to the angle of reflection.
Sorry, let me just one more time. Hold on.
And go, and so on, and so on. And these are all possibilities.
And every single one of these paths has their own little arrow. So what we can do is we can look at all those arrows and see where they line up.
Okay.
And so if I turn on this light, that's exactly where you see it reflect, so that the angle of incidence is equal to the angle of reflection. But now what I'm going to do is I'm going to cover up that spot so that we no longer see the light reflect. And then I'm going to prove that Feynman is right, that really light also goes like this. It's just that most of the time, those effects are canceled out. Now, that sounds impossible, right? But let's zoom into this tiny piece right here. Then we see all these different paths, and all the arrows just go around and around in circles. So when you add them up, they all just cancel out. But what if I cover up about half of them like so? Well, now, when I add up those arrows, you suddenly do see a large resulting arrow. And so, if I can somehow cover up this mirror in many, many tiny strips, then I should be able to get the light to reflect like this. And I can do that with this piece of foil right here. On this piece of foil, there are about 1,000 lines per millimeter, and that should be enough to get this effect. So,
holy fuck. Wait, hold on. I either had a big brain blast moment, or is this completely and totally fucking unrelated? Is this how polarizers work on lenses? Is that it causes destructive interference on just some parts of the... Just say yes, that makes me feel good. Okay.
Oh, let me turn off the lights. So let's see. I'm gonna turn it on in 3, 2, 1. We see it! We see it! Ah! That is so cool. It actually looks a lot weirder than I was expecting it to. I was expecting more like one spot, but there's many, many spots where it's reflecting. Ooh, okay. Okay, and just to show I haven't been cheating you.
Okay, and then where's my physics guy in YouTube chat? Because you mentioned that harmonics here work similarly as they would like in music for sound waves. So like this light that's being created here, is this kind of like blocking the fundamental frequency, and then this is your first harmonic? Those are the words we would use in music. So this would be the fundamental is your strongest point, but if you block the fundamental, then the next point of coherence would be your first harmonic. Is that what this would be here? Where's the guy?
Right underneath is my finger. And even with the light on, you know, we see the light reflect. And if we remove the cover, then what do we see? Yeah, we see exactly the normal reflection where it's always supposed to go, which is right there. And then we've got now all these extra reflections, all these extra bits where the pattern just lines up. So
wait, I didn't get that at all.
On you.
Wait, am I
right
retarded?
Underneath is my finger. And even with the light on, I've been cheating you.
Hold on.
Right underneath is my finger. Okay. Okay, and just to show I haven't been cheating you, right underneath is my finger. And even with the light on, you know, we see the light reflect. And if we remove the cover, then what do we see? Yeah, we see exactly the normal reflection where it's always supposed to go, which is right there. And then we've got now all these extra reflections, all these extra bits where the pattern just lines up. So
wait, I'm retarded. I don't understand what the... Wait, why do we have to block this light in the first place then?
Very, very cool. When I was talking about this with a friend, actually, he said, yeah, but you're using a diffraction grating. That's kind of like cheating, because you get all these other reflections right now. And this light is just going in all directions. And so...
Top right, you can see the reflections of the red light. Yeah, I guess. I see it up here. Wait, why do we have to block the middle one, though? Did that matter?
There's one other thing I've been super, super curious to try. I also want to do this with a laser, where I shine the laser right next to it, and then if light does take every possible path, we should also see it come off here. It probably shouldn't work. I actually have a laser right over here, and we can see when I shine it.
Oh my God! Hold on, I'm sorry. I feel like there's just a bunch of random facts I've had in my head that I feel like make more sense now, because I've heard like, well, why do lasers work? And in my mind, I'm thinking a laser, somehow you just are shooting single electrons or whatever. But then I've read words like, oh, well, they use coherence patterns or bullshit or whatever. But somehow I'm guessing the slit at the end of a laser and the frequency of the light is just that it causes some kind of destructive interference around everything except for that central point. Is a laser basically just some light frequency that is utilizing destructive interference in such a way that you only see the single point of... Is that how that... Is that... Wikipedia. Lasers. Why do they shine in one only direction? If you shine a laser into a screen or while you see a red dot and nothing else, I'm sure lasers can be very... Most lasers are a narrow beam, but all have some divergence. The only rays which are emitted are ones which are traveling nearly parallel to the cavity. Laser diodes have short cavities and have up to 30 degree divergence, and they must be collimated with a lens. The fuck does that mean? Made accurately parallel. But how can they be made parallel? Wouldn't they all come out as waves at the end? Isn't that the... Well, first of all, if it isn't a straight line, light is a wave and all waves diffract, so it does spread out. There's a theoretical limit to how little a wave can spread out, and that's called the Gaussian beam. Gaussian beam? In an ideal beam, which is a good size or a good quality laser, we'll get very close to it, the angle it spreads out is given by wavelength divided by pi times aperture size. This is the size of the spot, but there is a small amount that radiates in every direction as well. Notice that as the aperture size decreases, the angle increases. So as a point source, it really would spread in all directions equally, but it isn't a point source, it's an aperture of finite size, and the front of point sources produces interfere constructively and destructively. I'm gonna assume what I said is kind of correct, but it's just a little more complicated. Close enough, okay?
It really does just go to one spot. And you can see where that spot is. It's right over there, which is about the same place where we had our reflection.
Okay.
And you can also see right now, if we look at this view, that you cannot see the laser light at all, right? Like I could see the laser, but I have to bring it down all the way over here. And then I'm able to sort of see the light. But if I just put it up here, you can see the reflection. Now, what I'm going to do next is I'm going to put this foil, this magic foil, and I'm gonna put it over here.
Okay.
Oh, and we can turn off this. And now let's see what happens when I turn on the laser. Wait. No way. No way. It works! It works! Wait, what? Look where the laser is going. Oh my God. It actually works.
I don't understand what we're excited about, but...
What? What? This is definitely the coolest demo I've ever done. So what I was doing is I was holding the laser.
Okay.
And I can show you right now. I was shining it down like this.
I see that.
Way off, and you could still see it reflect. But if I take this away, it disappears. And if I put this back, it appears.
So that shows really that we
It's proof that the laser light is taking all paths possible.
cannot get rid of the area which gives zero, that it really...
It disappears. And if I put this back, it appears. But if I take this away, it disappears. And if I put this back...
Oh, because he's aiming the laser here. But if he puts this like, this polarizer film here, it looks like the laser beam is only here. However, it is existing in some form in other paths, and then this helps us see it here like that, right? So this is somehow fucking with the ordinary interference pattern or whatever, that's something like that. Already close
it appears.
So that shows really that we cannot get rid of the area which gives zero, that it really is canceling out.
Wow.
And if we do clever things to it, we can demonstrate the reality of the reflections from this part of the mirror.
Thanks, dude.
So light, and by extension...
Damn, how did you do that? Was that a different polarizer thing, or...?
So light, and by extension everything, really does explore all possible paths. It's just that most of the time, the crazy paths destructively interfere. That's because the actions of nearby paths change rapidly. Now, I've studied physics for most of my life, and I feel like I never really appreciated how important action and the principle of least action are. But now I think I finally get it. And I finally get why if you ask theoretical physicists what they're working on, they'll rarely talk about energy or forces. Most of the time, they'll talk about action.
Nobody in particle physics approaches particle physics from a viewpoint other than least action. But we teach physics historically, and least action is almost like the new kid on the block for understanding physics. And so yeah, we build up to it. But in reality, I think life's a lot easier once you realize there's this underlying principle.
Absolutely.
Because when you do, then all you have to do is write down the correct Lagrangian, so you get the right action, and out come the laws of physics. So you've got a separate Lagrangian for classical mechanics, for special relativity, for electrodynamics, and so on.
It's a single mathematical framework. Like once you've learned it, then you can apply it in different places in exactly the same way. The hunt for the theory of everything, right? The thing that will encompass all of physics. In reality, what people are asking is, what is this Lagrangian that can spit out all of the laws of physics in this universe? That's really what they're asking. At the moment, we haven't really found that, right? Because we can sticky tape things together, but we don't know if that's the proper mathematical structure. So that's what.
Okay. Okay, I feel like this guy's videos are very dense sometimes. Jesus.
To make a laser, all you need to do is give a big collection of atoms enough energy so they're excited and ready to emit light.
Okay.
Once one of them spontaneously emits a photon, it'll stimulate some of the others to do so, and you get a nice cascade of illumination. But instead of letting all the light escape, it's more powerful to trap it between two mirrors and let it bounce back and forth through the atoms. All that passing light will stimulate them to emit even more light, and as long as you keep on re-exciting the atoms, they're happy to go on emitting light forever. But why do the atoms emit light just because another photon passes by? It's actually pretty simple. Imagine flipping two coins. They can either be in the same state or in different states. But photons aren't like coins. No matter how hard you try, you can't tell one apart from another. So in a photon flipping experiment, that means there's only one way for them to be in different states, but two ways for them to be in the same state. So they're more likely to be in the same state. And in general, this implies that photons always want to be like other photons, to have the same phase, polarization, and go in the same direction. And what's more amazing is that if a solitary photon passes by an excited atom that could emit another photon, there's a good chance it will emit one, because the two photons want to be together, even before the second one exists. So once you have all these friendly photons bouncing around between the mirrors, you can just open up a little hole at the end and let out a blinding stream of coherent light, a laser beam. To see lasers in action?
Okay. Sorry, hold on. Oh, like there are more videos on this. Small
Here I'm
videos.
playing around with polarized light.
What are you doing?
Sunlight is unpolarized, so it doesn't really matter what angle that if I use a polarizing filter. If you have two filters and they're polarized in the same direction, then essentially nothing too interesting happens.
Okay.
If the polarizers cross, then essentially light making through one filter is horizontally polarized. Then the next filter only lets through the light that's vertically polarized, so cumulatively nothing makes it through. This is used to have adjustable filters in photography fairly often. Now, something really interesting starts to happen. And in fact, a quantum effect begins to kick in if I ask three questions. So surprisingly, the answer I get depends on the order that I ask the questions. So if I have a horizontally, diagonally, and then vertically polarized, I get a different answer than if I ask horizontal, vertical, or horizontal, vertical. So in between, I actually get a lot more light transmission than you'd expect. And this is an angular dependent sort of transmission. So it has to be between the asking the horizontal and asking the vertical question that I ask this diagonal question. And this is really a quantum effect. So if I ask the photons the same questions in a different order, I actually get a different answer, which seems a little disturbing to me.
Wow. That was AI, by the way. Okay. All right, we're done with physics for now. Okay. Sorry.